Welcome to today's talk in the IMSC Diamond Jubilee lecture series, which is a part of the 60-year celebration of IMSC. As our distinguished speaker today, we have Professor Parimala. She is from Emory University and works in number theory. She is very well known in the mathematical community for her work on quadratic forms and related problems. Today, she will be speaking about quadratic forms over function fields.
So let me begin as she introduced me. I like quadratic forms very much. So let me just define what the objects I'm dealing with and the problems we are interested in, what is known and where we are going with respect to these problems. So, quadratic forms. So please feel free to ask questions if some notation or something is not clear or whatever. So, quadratic form. Over a field K. So K is a field, and today we'll assume that the characteristic of the field is not equal to 2. Mostly we'll be discussing characteristic 0 fields in today's discussion. Okay, so what is a quadratic form? It is simply a homogeneous polynomial of degree 2 in certain number of variables, and from linear algebra we learned that any such form you can diagonalize because the characteristic is different from 2. So I'll assume without loss of generality, quadratic form looks like a1 x1 squared. I have diagonalized it with respect to some basis of the underlying vector space an xn squared. Let me assume that all the ai's are in K star. This is the assumption that this is so-called non-degenerate quadratic form. Okay, so these are the objects I'm interested in. This is called quadratic form in n variables. Okay, and we say, just for short, isotropic. This is the whole theme of today's lecture. So you take a quadratic form, you can look at it as a function on Kn, right? On the affine space Kn, if you substitute n for x1, x2, xn values of k, you get a value in k. So it is a form on Kn. It's quadratic. Okay, and so call this Q. Q is isotropic if it represents 0 non-trivially. Q represents 0 non-trivially. Okay, what does it mean non-trivially? Obvious notion. If you put all the xi's 0, obviously this form has value 0. That we don't consider as a proper 0. So a non-trivial 0 is there is a substitution lambda 1, lambda 2 up to lambda n with values in k, not all 0, such that q of lambda 1, lambda 2, lambda n is 0. Then you say that the form is isotropic. This is a shortening of saying that the form represents 0 non-trivially. Okay, so and then we have, so you can define an invariant called the U invariant of the field. Okay, so just for short, instead of each time repeating the whole thing, I'll shortly define U invariant to be the maximum of this n variables is called the dimension of Q, which is in this case n. It's a maximum of dimension of quadratic forms such that Q is anisotropic over K. You take anisotropic forms, take their dimensions and take the maximum of these dimensions. That you can call the U invariant. Of course it could be infinite also, right? So if you take the field of real numbers, you can take x1 squared plus x2 squared plus xn squared for any n. It is a sum of squares, it's not going to represent 0 non-trivially. Okay, so but we are going to look at certain fields for which this U invariant is finite. For instance, one example would be very good. So if you take K is C, okay, any a1 x1 squared plus a2 x2 squared, two variables is going to be isotropic because every non-zero element is a square, right? So what is the U invariant of C? Because every two-dimensional form has a 0. On the other hand, if you take a one-dimensional form, it is not going to represent 0 non-trivially. So U invariant of C is 1. This is the basic example, okay? And we said U invariant of reals and so on is infinite. So some other example where the U invariant is finite you have seen in your number theory class. What about finite fields? Assume that characteristic is not, it doesn't matter. What is the what do you know about quadratic forms over finite fields? It is characteristic different from 2, you can just write it as a1 x1 squared, a2 x2 squared, a3 x3 squared, and so on. And what do we know? Every dimension 3 form has a non-trivial 0. Okay, this is over a finite. This is a very elementary exercise, which is more or less combinatorial, counting squares, non-squares, etc. over a finite field. Little more. Okay, so if you take a finite field, U invariant of a finite field is 2. And a little further, if you go, if you know p-adic fields, p-adic integers, this is like QP, which is completion of Q with respect to a valuation given by the prime P. Okay, QP if you take, it has a p-adic integer ZP sitting inside, which is Henselian or complete, and ZP mod, it's a discrete valuation ring, and mod P, it is a finite field. Okay, if you use the Henselian property, it needs a bit of exercise to prove that the U invariant of QP is 4. See, every 5-dimensional quadratic form over a p-adic field has a non-trivial 0. Not only QP, you can replace by any finite extension of QP, which is called a p-adic field. K over QP finite. Okay, so these are examples of fields with finite U invariant. And then some of you might have seen Minkowskis Theorem. Okay, if you want to go from the local situation to the case of number fields, so you have this famous theorem of Minkowski, which is Minkowski for rationals, and in general and Minkowski, which says if you take a number field, so it has a set of valuations. If you take Q, for instance, you have various valuations given by the p-adic valuations for each prime, as well as you have Archimedean valuation. You have the real completion, right? If you take a number field, you could also have completion as C or R or one of the p-adic fields, finite extensions. So these are the set of obvious completions of the number field at various valuations, both finite valuations as well as Archimedean valuations. And then if you take a quadratic form over a number field, the famous Minkowski says that if the form represents 0 non-trivially over all completions, okay, then it represents 0 non-trivially over the base field. Okay, this is a very powerful theorem. Okay, so if you want to test isotropy of a quadratic form over a number field, you just have to go to various completions. Over reals, we know how to check. You are starting with a1 x1 squared plus an xn squared. Over reals, what is the criterion? This form represents 0 non-trivially. What is the condition on the AIs? So when does it have a 0? This form a1 x1 squared plus a2 x2 squared plus an xn squared, where all the AIs are treated as real numbers. When does it represent? When does it not represent 0 non-trivially? All are positive, all are negative, then it's not going to represent 0 non-trivially. Only case in which it can represent 0 non-trivially is that it has a change of sign, right? So it's very easy to conclude when form over reals represents 0 non-trivially. And in the same way, even over the p-adic numbers, using this kind of Henselian property, it's not too difficult to check when a quadratic form represents 0 non-trivially or not. It is not that difficult exercise. So the local conditions are easy to verify, and therefore the theorem of Minkowski theorem states that K is a number field and Q is a quadratic form over K. Quadratic form over K. Then Q represents 0 non-trivially, represents 0 non-trivially if it represents so locally. If our Q is isotropic, if it represents 0 non-trivially locally at all completions, non-trivially locally. So this is a classical result, uses class field theory and so on. So starting from here, suppose K is totally imaginary, that means it has no real ordering. So the only completions of K in this case are either complex numbers or p-adic fields. Over p-adic fields, every dimension 5 form is isotropic. Over complex numbers, even every 2-dimensional form has a non-trivial 0. Therefore, what can you say about the U invariant of K? In this case, it is at most 4, right? Because every 5-dimensional form needs to represent 0 non-trivially by this result. But you can show it as 4. There are 4-dimensional forms which are anisotropic. This can be checked. So U invariant of a totally imaginary number field is in fact 4. You can produce rank 4 forms which do not represent 0 non-trivially. It's a good exercise over Q to construct forms, rank 4 forms which do not have. Just take 1 P, Q, PQ for suitable primes P and Q, then you can check when it represents 0 non-trivially. All right, so far good. So we have this discussion about certain classes of fields for which the U invariant is finite. So then the next discussion is, so when you pass from a field to rational function field in one variable. Okay, this is just the rational function field in one variable, which is a ratio of polynomials. This is a field of ratios of polynomials. Okay, so this is the most obvious field extension of K, namely the purely transcendental extension in one variable. So suppose you know that the U invariant of K is finite, like K is a totally imaginary number field. What can you say whether U invariant of KT is finite? This is very important in the case of when you move to the geometry of varieties. We are looking at quadratic forms over varieties and so on. You have a parameterized family of quadratic forms, and you want to know whether the family generically represents 0 non-trivially or not. Okay, so this is a very natural question passing from K to KT. So question is, so U invariant of K is finite, and suppose we also assume that not only U invariant of K is finite, and U invariant of L is finite for every L over K finite. Okay, suppose you assume that for all finite extensions, then is U invariant of the KT finite. Okay, so it's just like in the case of number fields, a finite extension number field is a number field. So if it is a totally imaginary number field, U invariant is 4 for all extensions. Can you say something about the U invariant of KT? This is a big open question, open. See, one does not know an answer to this question. Even in the simple example of if you just take Q and you want it totally imaginary, let us assume Q root minus 1, which has no ordering. And then you take rational function field in one variable over Q root minus 1t. We do not know whether quadratic forms in large enough number of variables represent 0 non-trivially. This is yeah.
Finite.
What? Oh, okay. So there's some different phenomenon happens. It's a very good question. Suppose you take a finite field. And of course, if you adjoin one variable, it's a global field of positive characteristic. You have a Hasse principle there also. So there every 5-dimensional form is isotropic. Okay, but you can also take any number of variables. Okay, so here we know that maybe 2 to the power n or 2 to the power n plus 1 will be the U invariant. This phenomenon is because this is a FQ is a C1 field. Okay, which is a very special property. Okay. So it is in terms of forms of degree n in some I variables. This is a C1 field. So when you adjoin n variables, this is Cn plus 1 field. So any form in large enough, any quadratic form in large enough variables with respect to n has a non-trivial 0. Okay, this is a special phenomenon where you can say what happens when you go to function fields. If you start with a field which is Ci or C1. Ci for instance, okay, then you have an answer. But the kind of fields we are looking at, like number fields and so on, there's no such property. So these are pretty open questions till today. For this very basic example of q root minus 1t, we do not know whether the U invariant is finite. And in fact, a more bold question is question prime, or maybe it's even a sort of believed to be a conjecture. So is U invariant of KT every form in 9 variables, does it admit a non-trivial 0? This is a finer question, and not only KT, you can also replace KT, rational function field in one variable, by you take a totally imaginary number field. You can take a field of transcendence degree 1 over k. Okay, finitely, you can take function field of a curve over a number field. Not necessarily rational function field, you can also take C over k as a curve. You can ask the same question, is the U invariant bounded or U invariant is 8? Why am I asking more and more serious questions when even the basic question is unanswered? You do not even know the finiteness. I mean, the motivation is the following. So if you replace a number field by a p-adic field, something like QP, or its finite extensions. We know that QP, every 5-dimensional quadratic form has a 0, and its U invariant is 4, right? So in this case, so when you pass from QP to QP of T, or even QP of a curve, or you can even replace or K of C, where C is a curve and K is a finite extension of QP. Finite. So the function field of a curve over a p-adic field. Okay, this is a typical example. Here it is true that U invariant is 8. Every 9-dimensional quadratic form, instead of a number field, you go to the completion. There it is true that when you go to function field in one variable, the U invariant is 8. It is, you will believe that this is known for a long time. It's not known for a long time. It was as late as maybe 2007 or 2008, where the first proof appeared for the non-dyadic p-adic field case. This was proved by Suresh and myself for p not equal to 2, and later on there was a uniform proof for all primes due to Heath Brown, and using his paper, Leap deduced that the U invariant is 8, and this is a uniform proof, but completely different methods. And we use some Galva cohomology methods, which I'll explain in the rest of the talk. But later on, we came out with a Galva cohomology proof, which includes also the prime 2, but that was later than Heath Brown and Leap. So because in the local case, replacing the number field by a completion which is a p-adic field, there we know that if you take a function field in one variable over the field, then every 9-dimensional quadratic form has a non-trivial 0. Once this is known, the next natural question is, this is open for the last 20 years after it is known for the p-adic fields, whether a similar question, whether a similar answer you can expect. But so far there is not much progress even concerning finiteness of the U invariant. Okay, one does not know. And it's a challenge. I mean, just as, because I adopt a method using Galva cohomology, maybe there are analytic number theorists who can use alternate techniques, come up with a proof. I'll be very happy if this forum brings forth the proof of this answer to this question. Yeah, so let me begin by one way we try to attack this question. This is via Galva cohomology invariants of quadratic forms. So let me explain what are the invariants we are looking at. So first, what are the Galva cohomology groups I'm looking at? What is Galva cohomology? It's very simple. So K is suppose K is a field and K is a field and K is the separable closure, and this is the absolute Galva group of the separable closure over K. This consists of the union of all finite Galva groups. Okay, the inverse limit of finite Galva groups. So this is a profinite group. Profinite, it has a topology, profinite topology. And suppose you have a M is a discrete gamma module. Discrete means M has discrete topology, gamma has profinite topology, action of gamma and M is continuous. Okay, this is a generality. I'll come to a very simple example. Then you have this Galva cohomology groups with values in M. These are defined. These are limits of, you take all the finite Galva extensions G, finite quotients of the full gamma. You have the full Galva group, you have the finite quotients consisting of Galva groups of finite extensions, and you take the corresponding G, and you take the invariants of the quotient, this is G is gamma mod H. So the invariants under H if you take. So this is finite group, this is a module, this is just a discrete G module, it's a usual cohomology. Cohomology of a module or a finite group. You take these cohomology groups and you take the direct limit of this. Okay, this is simply the Galva cohomology. If you want to just, so anyway, I'm going to look at only one module, namely Z mod 2Z. There can be only one action of anything on Z mod 2Z, and therefore I'm just going to look at, so this sometimes we call HIKM. Just K is the field and it's a Galva cohomology. I'm just going to look at HI of K Z mod 2Z. This is the only group I'll be interested. You can forget all the previous definitions. So these are the cohomology groups, and I'll give you a flavor of what these look like. H0 is always Z mod 2Z. The invariance, everything action is trivial, so Z mod 2Z. And what is H1? There is a Kummer sequence which describes H1 as simply the group of square classes in K. So I will not explain the details, but it is an easy exercise in Galva cohomology that H1 gives the square classes in K, and H2, this again is from the Kummer sequence, H2 K Z mod 2Z. This gives the two torsion of the Brouwer group of K. So the Brouwer group of K is a group associated to a field, one of the invariants which is very widely used both in arithmetic and geometry to discover various facts about the fields concerned. So how do you construct the Brouwer group? We have certain classes of algebras called central simple algebras. They are forms for just the matrix algebra. An algebra which the algebraic closure is isomorphic to Mn of K, the matrix algebra, such algebras are called central simple algebras. Then these algebras under tensor product forms a monoid, and then you need to invert them, so you introduce something called Brouwer equivalence, where the matrix algebra itself is declared a trivial algebra. Okay, then under this equivalence, the classes of algebras forms a group, that is the Brouwer group of a field. It is a very, very important invariant both from arithmetic point of view as well as geometric point of view. So this is the Brouwer group. Two torsion means elements for which 2 times the element is 0. That is the two torsion subgroup. So the H2 is the two torsion subgroup, and similar way Hn of K Z mod to Z, there's no description. You can have the higher cohomology groups, and I want to say that quadratic forms have invariants, successive invariants. I'll write quadratic forms have successive invariants. I will describe what I mean by successive invariants in Galva cohomology, in Hi of K Z mod 2Z. So what do I mean by this? So first of all, given a quadratic form Q, so dimension of Q. So dimension of Q, I already said what it is. It is number of variables involved. It is just n, but I will take dim2, which is the n mod 2. You take the class of n mod 2. It is even or odd, that's all that matters. This is Z mod 2. So given a quadratic form, you decide it is even dimension or odd dimension. This is the first invariant which lands in H0, which I described here. Okay, and then suppose dimension Q is even dimensional. Let me define this can be defined more generally, but let me define the discriminant of Q to be, what is the discriminant? I have a diagonalization a1 x1 squared plus an xn squared. You can take the product of the, it is called, you can represent it, you can think of it as a diagonal matrix a1, a2, an. You take the determinant of this matrix, okay? This is just a1, a1, a2, an in k star mod k star squared. If q is a1 x1 squared plus an xn squared. This is the discriminant invariant of the quadratic form. Why am I saying mod squares? Because if I change the representation, you can take a change of variables and you can write it as a diagonal form or whatever form in a different way. Okay, there are many different ways to express, but the determinant will change only up to squares. Will not change. It is invariant under squares. Okay, if you take two different representations, the determinants will differ by a square because it's related by the congruence of symmetric matrices. So only a square factor remains. So the discriminant is defined mod squares, but I want the sign discriminant, so I'll put a sign also, n into n minus 1 by 2. I will explain why this sign, because there is some form which is absolutely trivial from the algebraic theory of quadratic forms. This is just the hyperbolic form, x1 squared minus x2 squared. Okay, this is the hyperbolic form. It represents 0 non-trivially, and this we want to neglect as trivial form in whatever sense. And when you look at this form or sums of these forms, you want all invariants to be 0. Okay, so this has even dimension, so the first one will not exist. And what is the determinant of this form? It is just the determinant is minus 1n. But however, if you take the sign into consideration, it becomes plus 1. So you neglect all the invariants of hyperbolic forms. That is the point of these signs and so on. Okay, and then suppose Q has even dimension. This is what I mean by successive invariants and even dimension and trivial discriminant. Then the Clifford invariant CL of Q is this is simply, there is given a quadratic form, there is something called the Clifford algebra associated to the quadratic form, Clifford algebra of Q, and it is a central simple algebra over Q which has an involution. It belongs to the two torsions of the Brouwer group of Q. Okay, what is the Clifford algebra? You take the tensor algebra and go modulo the two-sided ideal generated by the relation V tensor 2 minus QV. Okay, this is the Clifford algebra. Okay, so that you can prove is a central simple algebra or an algebraically closed field. This is in fact a matrix algebra, and you take the class of this algebra in the two torsions of the Brouwer group. This is the Clifford invariant of quadratic forms. Well, we have defined all these invariants, and if these invariants are 0, you can define the E3 invariant, and if up to E3 the invariants vanish, you can define the E4 invariant, and so on and so forth. Okay, higher invariants can be defined for quadratic forms, and in fact in a very remarkable paper, Milner proposed certain conjecture which says that, so all these invariants, first of all, you know how to define up to, let me, instead of having, you have ENs for all n, let me call it E0 and call this E1, call this E2, and the higher invariance of En of Q. But after 2, maybe 3 was already defined in the 70s, E3, but after that even the definition of E4 is not clear. But Milner gave a recipe, this should be the definition of higher invariance, which has to be proved, and he said the whole set of invariants completely determine the isomorphism class of a quadratic form up to adding hyperbolic planes. Is it clear? Up to hyperbolic planes you can determine the quadratic form if all the Galva cohomology invariants are the same. This is Milner conjecture. First of all, he defined the invariants as what it should be. He didn't define, but he said these should form invariants. He didn't prove. And he said these should completely characterize quadratic forms. This is the so-called famous Milner conjectures. This what I am stating is a quadratic form version of, there's a k-theoretic form of Milner conjecture, but this is the quadratic form or theoretic form of Milner conjecture. So-called Milner conjecture. So what I stated is a quadratic form theoretic, and now it is a theorem. First, the k-theoretic form is solved by Vygotsky, and then the quadratic form version is not immediate from the k-theoretic form, but this proof was given by Vygotsky. I will call it OVV. It is unfair to give just letters. This is Orlov, Vishik, and Vygotsky. The three of them fixed a proof for the quadratic form case, and the theorem is simply that the invariants form a complete set of invariants for quadratic forms. So you have a classification of quadratic forms by invariants. Question: you have a question about quadratic forms and invariant for fields associated to quadratic forms. You know all about quadratic forms in terms of Galva cohomology. Can you give a description of the U invariant in terms of Galva cohomology? Okay, or at least describe. Okay, this is a very valid question. But the invariants are in Galva cohomology groups, so you need some facts about Galva cohomology groups to derive facts about quadratic forms, right? So you should understand the invariant groups in order to understand quadratic forms, right? Isn't it clear? I mean, you have invariants in a group. If you understand the group, you can say something about forms. Okay, so for that, towards this is the strategy. So what do we have to know about this Galva cohomology groups? Let me just quickly say some basic things. See, in fact, one of the consequences of Milnor conjecture is that, so if you take Hn(k) Z mod 2Z, this Galva cohomology. I didn't say much about this. This is a limit of certain things, but there are some fundamental elements in this. These are called symbols. So when you take H1, you take any square class in K star mod K star squared. This group K star squared, this is just H1 K Z mod 2Z. This is H1. And you can take a cup product of these H1s n times, you should get an element in Hn, because Z mod 2 tensor n, because the action is trivial, it is Z mod n. So you can take cup product A to An, cup product of one symbols here. This is an element in Hn(k) Z mod 2, and this is called a symbol. Such elements are called just symbols in Galva cohomology, okay? Those which are cup products of one symbols. And in fact, Vygotsky's result, Vygotsky, so every element psi in Hn is a sum of symbols, Hn(k) Z mod. This is from the fact that the quadratic forms mapping onto these things will give that. I didn't state precisely Milnor conjecture. In fact, it's one of the consequences is a sum of symbols. Sum of symbols. So this is a fact, and how many symbols is the question? Okay, so this is a very nice fact that if you take H2K Z mod 2, it is the two torsion of the Brouwer group. If you take a number field, okay, the two torsions of the Brouwer group is simply quaternion algebras, right? There is no bigger algebras than quaternion algebras. Quaternion algebra, which is given by I squared equal to A, J squared equal to B, Ij equal to minus Ji, in fact corresponds in the Brouwer group, this quaternion algebra. See this basic structure. See I squared equal to, this is a generalization of the Hamilton quaternions, J squared equal to B, Ij equal to minus Ji. If you take this four-dimensional algebra, this corresponds, this is a central simple algebra of dimension 4, this corresponds to the symbol A dot, A cup B. Quaternion algebra corresponds to a symbol. So everything in H2K Z mod 2 is a symbol over a number field. This is not a trivial, but it is arithmetic, okay? So you know that these are the kind of facts we need to conclude something about U invariants, okay? Let me just state, so what we need, okay? So I'll state as a result, which is not too difficult to construct a proof using Vygotsky's theorem. Namely, I'll state this is the passage between, the connection between U invariant and Galva cohomology. So statement. So let field K satisfy the following conditions. The following. First, so the Galva cohomology groups with coefficients in z mod 2z, these vanish for all n sufficiently large. Suppose all these Galva cohomology groups are all 0 beyond a certain level. Okay, this will be guaranteed if your field has certain cohomological dimension finite property. I will come to this condition. And secondly, so for every there exists a big M, integer M, such that for every psi in any of these non-vanishing ones, hi k z mod 2z, I less than or equal to n, say n plus 1 say. Up to n, you have non-vanishing classes. Psi is a sum of at most m symbols. Okay, the symbol length is bounded. This is what. Okay, so every cohomology class is a sum of at most m symbols for these finitely many non-vanishing classes. Okay, so if this happens, then U invariant of K is finite. So we have some sufficient conditions in terms of U invariant being finite in terms of, first of all, this vanishing of this for beyond a certain level, and all the elements in Hn, we know they are all symbols, but they have bounded symbol length. Okay, then it's not too difficult to get it from just one word about it is, suppose you have a sum of symbols. Okay, then the quadratic form which maps to that sum of symbols. If you take one example, if you take a1 dot a2 dot an, then there is a quadratic form with this as an invariant, and that quadratic form is the so-called Pfister form, minus 1 minus a1 tensor. You take the diagonal tensor product of these two binary forms, tensor 1 minus an. This has the En invariant, precisely the cup product of n symbols. Namely, what is the dimension of this form? This is a tensor product of vector spaces of dimension 2 with these forms 1 minus a1, tensor 1 minus a2, tensor 1 minus an. It has dimension 2 to the n, right? So you have a fixed quadratic form with a given symbol. So if everywhere there are bounded symbols, you have representatives which are quadratic forms with those as invariants. And then you subtract out a given form, these representatives, then you have all the invariants 0, the form is 0. So the form should have certain bounded dimension. It could be very large, but you have a bound. Okay, that is the idea of the proof of this statement. And you may think this may not be the only way to solve the problem. Maybe there's another way. These may not be necessary. Then why are you trying to prove these things? But these conditions are also sufficient, except you have to refine it for all finite extensions. Some conditions are needed. Basically, they are also necessary and sufficient for the U invariant to be finite. So you have to prove these if you have to ever prove the U invariant of the field is finite. Okay, so you have a complete criterion in terms of all these Galva cohomology groups, how to bound the U invariant. All right, any questions so far? Okay, so let us come back to our, so far is generality for any field. So let us come to our favorite field. K is a number field, totally imaginary. Imaginary number field. And C over K. C instead of KT, I can as well take any curve. We can assume it's integral curve, geometrically integral, whatever you want. Smooth, integral. And so on, and you take K, F to be the function field of this curve. So this is the basic curve for which you want to compute the U invariant. So with respect to these properties, what do we know about for this field? At least one thing is good. First, these fields, if you take a totally imaginary number field, okay, it has cohomological dimension 2. This, if you read the Say's book on Galva cohomology, you will find that cohomological dimension of a totally imaginary number field is 2. And the cohomological dimension behaves well with respect to function fields. So the cohomological dimension of function field of a curve or a totally imaginary number field is 3. Okay, if the cohomological dimension is 3, precisely H4 onwards, all the cohomology groups vanish. Okay, so Hn of f z mod 2 is 0 for n greater than or equal to 4. So we don't have too much to bother about. So what are the groups we have to bother about to have finite symbol length? H1 is always single symbol, right, because it's just class of an A. H2 and H3 are the only two groups for which we have to bound symbol length, right? Clear? And we have this following beautiful theorem of Suresh, that if you take H3 of F Z mod 2, here every element is a symbol here, not even a sum of bounded symbols, every element is a symbol, consists of symbols. So the bound is 1 here. Every element here is a symbol. Very good, so H3 has bounded symbol length. So we are left with, therefore, question. So H2F is H2F C mod 2 is it of bounded symbol length, So the question reduces, what is H2? H2, as I said, is the two torsion of the Brouwer group of F. So this is a problem on the Brouwer group, okay? So that question is equivalently, I'm not saying this is an obvious equivalence. So H2 is the same as the Brouwer group of two torsions of the Brouwer group, H2F C mod 2. Z is just two torsion of the Brouwer group of F. So this condition of bounded symbol length can be stated as every alpha in two torsion of the Brouwer group. You know, we recall two torsion of the Brouwer group basically consists of, first of all, it consists of central simple algebras which are order 2 in the Brouwer group. And using this even Mercurius theorem, it is a tensor product of quaternion algebras. Every element in the two torsion is a tensor product of quaternion algebras. And this says that what is the index of an algebra? So alpha is in the Brouwer group of F. It is represented by a central simple algebra. What is the index? Or you can even represent it by a central division algebra, because by Wedderburn theory, every central simple algebra is matrix algebra or a division algebra. What is the index of alpha? You just define it to be, this D is a form for the matrix algebra, so the dimension of D is a square, okay? Because MNK, what is the dimension of MNK over K? It is n squared, right? And this is a form for the matrix algebra, so it is a square. You take this. Index is the square root of the dimension, and of course period is just the order of alpha in Brouwer group of F, okay? These are the notions of period and index. Here we have period is at most 1 or 2. So every alpha n has bounded index. That means that is there exists n such that index alpha is less than or equal to 2 to the power n. Okay, there is a fact that the prime factors of index and exponent are the same. You want to prove that every element in the two torsion of the Brouwer group, which is represented by a central division algebra, has index at most 2 to the n for a fixed n for all the elements in. So essentially you are going to bound indices of central simple algebras or central division. This is a classical question, okay? So the entire U invariant boundedness reduces to this single question whether the two torsion of the Brouwer group has bounded index, okay? So this is where it reduces to. And maybe I have some 15 minutes, 1 hour. So I will be a little technical, but you can object, raise your hands, whatever at this point. So this bounded index problem, so we have this bounded index problem for F. F is function field of a curve. So F is the function field of a curve or a totally imaginary number field, okay? C over K is a curve. You have this integers in K. Okay, C is the curve over K, smooth projective, say. You can spread it as a model over O, and you can assume that C is regular proper over O, the proper model, because C is projective, you have a proper model over O, over the integers. You can spread it out to a regular model, okay, and so you have this C, and then this C, and then you have this F. The generic point, you have the curve and the model, you have this situation, and you have this Brouwer group of C, the model. See, just as I defined Brouwer group of a field as central simple algebras and the classes and so on, you can define the Brouwer group of a scheme in a similar way using in a good scheme in terms of Asmai algebras, or you can also describe it purely in terms of ethyl cohomology. H2 GM is the same as H2 XGM, okay, and that could be the definition of the cohomological Brouwer group of a scheme. Okay, so all these gadgets can be defined for a scheme. So Brouwer group of this you can show is contained in Brouwer group of the curve, is contained in Brouwer group of F. So this is a subgroup of the Brouwer group of F, and why I am mentioning this is that it is the following, the reduction of this problem to a particular case, so which is the theorem of, is it okay, the audio? Huh?
You can speak a little.
Yeah, like this. Is it okay? You can hear? All of you? Yes? Yeah, okay. So there is a reduction, there is a theorem of due to Lieblich, Suresh and myself. So we have this following reduction. In this case, so for every curve C over every number field K, so two torsional of the Brouwer group of KC has bounded index. This is our problem, right? When does this have a bounded index, right? This was the goal. If the two torsion of the Brouwer group of the unramified classes is for every C, I mean all these criterions are there for every K and every C. So for all curves over K, the two torsion of the Brouwer group elements will have bounded index, provided for all curves K and for all models, okay, you take models. These are very much smaller group. This has bounded index. Okay, if you know a bit of ramification, it says that this Brouwer group of C is precisely those elements of the Brouwer group, the function field, which have no ramification on C. It comes from the Brouwer group of every discrete valuation ring supported on C. Okay, so you reduce the whole problem of Brouwer group of the function field to something very nice, Brouwer group of a model. Okay, so this is this quite non-trivial reduction using some kind of twisted sheaves and so on. A lot of machinery goes into this. All this is all developed by Lieblich, this question of bounding indices of unramified classes in terms of certain twisted moduli spaces. So we reduce the problem to the unramified Brouwer group. So here, so we just need to, you have to take a curve over a number field and a model, regular smooth proper model over O, and we are interested in whether the two torsions of the Brouwer group of the model has bounded index. All right. So here we have a conjecture. V means I and J. I think we pose it in the paper. So from now on we have certain things to. So this is joint with Jaya Iyer. So the conjecture is the following: for anything in the unramified Brouwer group with the same notation as above. So for anything, doesn't matter two torsion, index alpha is period alpha. Just like in the number fields, we believe that for all unramified classes, the index is period is true. Okay. So this is the conjecture. If this conjecture is true, we are done. Much more happy than needed, because we needed only bounded index. We expect period equal to index. I'll tell you why we expect. You know, if you just take, instead of, you have a model for a curve or a number field, if you, instead of number field, let us take a positive characteristic global field, okay? That is function field of a curve or a finite field. In that case, the question exactly reduces to, suppose x over k, x over fq is a smooth projective surface. The parallel for the positive characters is projective surface, so this is a theorem of Lieblich, and this is the motivation for this conjecture. So if you take a smooth projective surface over a finite field, then for every alpha in the Brouwer group of the mod of this smooth projective surface, period equal to index. Of course, you have here some mild assumption that index alpha is co-primed to the characteristic. For all Brouwer classes which are co-primed to the characteristic, period and index coincide. This is the exact analogous conjecture for positive characteristic global field where it is proved. Okay, so we expect probably this is true, and we are nowhere near ending at the end of the proof of this conjecture. But so forget all the rest of the story about U invariants. This question of the unramified Brouwer group period equal to index by itself is an interesting question. So let us look at specific classes of curves. If you look at specific classes of curves and prove anything, you are not going to prove anything about U invariant, because U invariant you need all function fields, okay? So not enough to do for certain class, at least it will give you an idea whether we are in the right direction, okay? So the question is, so this is my project with Jaya. So we started looking at C over K is a hyperelliptic curve, okay, genus. So the question is, look at the class of hyperelliptic curves. Okay, so in this case, suppose we also assume that the curve has a rational point. So in this case, you can represent the curve as y squared equal to ft, possibly with degree of, suppose genus G is G. Then you can assume that degree of ft is 2g plus 2. So every curve, a hyperelliptic curve, admits a representation like y squared equal to ft, like this, which is a rational point. So you take this class of hyperelliptic curves, look at the class of unramified Brouwer groups over the model for this curve or a totally imaginary number field. Can you bound the period by index by the period, or what can you say about this conjecture? Okay, just this class. So we developed a method which uses certain, as I said, the period index bounds for unramified classes is related to twisted sheaves of moduli spaces. And there is a description of moduli spaces of rank 2 vector stable bundles, okay, over hyperelliptic curves in terms of pencils of quadrics, okay. Lagrangians inside the base locus of a pencil due to Ramanan and Deshale. And Ramanan wrote down a rational version of this, and we wanted to use it to prove something general for hyperelliptic curves. However, what we can prove is the following, which gives a little glimpse of hope, but very little. So we have a theorem. So K is as usual totally imaginary. Genus 2. Every genus 2 curve is analytic. Genus 2 curve. Then and C over K model, any irregular proper model, then period equal to, the conjecture is true, period equal to index for alpha in 2 torsion of the Brouwer group of sigma. Okay, so we prove that the conjecture is true for genus 2 curves. This just probably gives a little hope what could happen. We have a strategy for higher genus, but we don't know how to execute the final proof of the main result. But at least genus 2 we have a proof that genus and the period and index coincide. Okay.
I think it's just not only for the 2 torsion, but the full Brouwer.
The full Brouwer group, the conjecture is, but the interesting aspect from quadratic forms is the 2 torsion, which we are happy if there is an answer here. But here we could prove just genus 2 curves, and it will be another topic of another talk, how you go about proving this for unramified Brouwer group, maybe next time. Thank you very much.